All right, now let's talk about another ensemble method known as random forest. So random forest is another fun tree pun. I think that decision trees are just the best for all the puns that they use. But basically, a random forest provides an improvement over bagged trees by way of a small tweak that basically decorrelates the trees. So as you can imagine, if I'm doing that process of basically pulling from, I've got one training data set, and I'm creating a lot of smaller training data sets from that, and then I'm creating a whole bunch of trees based on each of those training sets. And you can imagine each of those individual trees are going to be highly correlated, especially because we're sampling with replacement when we're doing our bootstrap. And so basically, the same people can be in multiple of these training sets. And so you would expect that those trees would end up being pretty similar, which means that they're highly correlated. And so we're definitely we're improving our variance of our predictions by taking that average. But when things are highly correlated, sometimes that can inflate the variance just a little bit. And so by decorrelating those individual trees, it actually reduces the variance even more when we average the trees. So like bagging, the process that we do is we start the same. So we build a number of decision trees based on bootstrapped training samples. So we still do that first part where we take our original training data and we resample it a whole bunch of times so that we get a bunch of not smaller, but we get a bunch of different training data sets. We have a larger number of training sets. So instead of just having one training set, we could do B training sets to try our decision trees on. But this time, each time the tree is split, instead of considering all predictors, like bagging, and so the way that bagging works is basically once you get to the part where you are fitting a decision tree, you're fitting it exactly the same way that you would normally fit a decision tree. And when you normally fit a decision tree, the very first step, this is a greedy method where the very first thing your tree does is it considers all of your predictors and then it finds the optimal spot and the optimal predictor to make a split. And so it takes all predictors that you've given it and it looks at what would be the predictor that would maximize our benefit or minimize our error. So instead of doing that, what a random forest is going to do, instead of looking at all predictors, it's going to randomly select M predictors to look at, and it's going to choose those as the split candidates from the full set of P predictors. So instead of using your entire set of predictors, you're just going to look at M of them, and you pick those M randomly. So the split is allowed to only use one of those M predictors instead of all P predictors. And a fresh selection of M predictors is taken at each split. So you eventually could potentially use all of your predictors, but you are just looking at M at a time. And so you can pick different M's, but typically you pick M to be approximately the square root of P or the square root of the total number of predictors. And so that's what we're going to do here. So just to make sure that we're kind of staying afloat with all of this, let's say you have 100 observations and 9 variables. If you were fitting a random forest, what would a good M be for that, given the rule of thumb that we just talked about? So I'll give you a second to flip back through the slides to determine that, and then we'll talk about the answer. All right, so if we had 100 observations, so N is 100, 9 variables, so P is 9, what would we pick if we were trying to pick a good M? So typically that M, or the number of predictors that you're going to consider at each split, is going to be the square root of P. So in this case, the square root of 9, it would be 3. So you could think through a diagram, kind of like what we drew before, to sort of think through the decision tree process for what's going on now that we're just randomly selecting 3 variables instead of looking at all 9. And so the process is going to be, first you would randomly select, so you'd randomly sample 3 of your 9 variables, and then among those 3 you'd see where an optimal, which of the 3 would optimally give you a minimized residual sum of squares, for example, if you're doing a regression tree, and at what point you should split it. And so you would create that split with that optimal variable, and then at the next decision point, you would randomly select a new set of 3 variables and again pick the optimal split, and so on and so forth.